Before we examine the global robotics race, we need to understand a fundamental challenge. How do you make a machine walk like a human? This is one of the hardest problems in engineering, and increasingly one of the most exciting applications of artificial intelligence. Walking seems effortless. You do it without thinking. But the moment you try to build a machine that walks, you realize how miraculous human locomotion actually is. Here is the key insight: human walking is controlled falling. Every step you take, you fall forward and catch yourself with the next foot. You are constantly on the edge of collapse. Your brain performs thousands of micro adjustments per second. Your inner ear senses balance. Your muscles respond instantly. Your eyes predict terrain. All of this happens below conscious awareness. For engineers, the first approach was something called static walking. The robot keeps its center of gravity directly over its feet at all times. It never falls because it is always balanced. This approach uses what we call the zero moment point, ZMP. As long as the ZMP stays within the support polygon formed by the feet, the robot will not tip over. Early Japanese robots like Honda's Asimo used ZMP extensively. The robot would shift its weight carefully, always maintaining perfect static balance. Traditional control theory, PID controllers, and trajectory optimization govern these movements. The problem with static walking is obvious when you watch it. The robot moves slowly, it looks unnatural, every step is deliberate and cautious. No one walks like that. Static walking also consumes enormous energy. The robot fights gravity constantly instead of using it. The motors work hard to maintain positions that a human would never hold. The breakthrough came from understanding dynamic walking. Instead of avoiding falling, dynamic walking embraces it. The robot falls forward and catches itself just like humans do. The mathematical foundation is called the inverted pendulum model. Imagine a broomstick balanced on your palm. It wants to fall. Your job is to move your hand to keep it upright. A walking robot is an inverted pendulum on legs. The body wants to fall. The legs must move quickly enough to catch it. Get the timing wrong, and the robot crashes. This is where AI enters the picture. Traditional control algorithms struggle with the complexity of dynamic walking. Machine learning offers a different approach. Let the robot learn to walk through experience. Reinforcement learning, RL, has revolutionized robot locomotion. In RL, the robot tries actions, receives rewards for staying upright and moving forward, and gradually learns policies that work. The key algorithm families include proximal policy optimization, PPO, and soft actor critic, SAC. These allow robots to learn smooth, natural gaits through millions of simulated trials. Deep reinforcement learning combines neural networks with RL. The neural network learns to map sensor inputs, joint positions, velocities, IMU data directly to motor commands. No human engineer programs the walking pattern. Simulation to real transfer, sim to real, is critical. Training in the real world is slow and breaks robots. Instead, robots learn in simulated environments like Isaac Gym or Mujoko, then transfer learned policies to physical hardware. The challenge with Sim to Real is the reality gap. Simulation is never perfect. Friction, motor delays, sensor noise all differ between simulation and reality. Domain randomization addresses this by training across many simulated variations. Model predictive control, MPC, remains important alongside learning. MPC simulates the next few hundred milliseconds, tries different control actions virtually, and picks the action that keeps the robot balanced. Modern systems often combine MPC and RL. RL learns high level gait patterns, MPC handles real time adjustments. The combination outperforms either approach alone. The sensors feeding these AI systems are crucial. Inertial measurement units, IMUs, contain accelerometers and gyroscopes that detect motion and orientation. Modern IMUs can sense changes in milliseconds. Joint encoders measure exact positions and velocities of each motor. Force torque sensors in the feet detect ground contact. Together, these create the proprioceptive sense, the robot knowing where its body is in space. The actuators, the motors that move the joints, face their own challenges. They must be powerful enough to catch a fall, yet precise enough to place a foot gently. Traditional industrial motors are designed for precise, repetitive motion. Factory robots move to exact positions and hold them. Walking robots need something different. Walking requires what engineers call compliance, the ability to yield to forces. When you step on an uneven surface, your ankle adjusts. A stiff motor would fight the ground and lose. The breakthrough was the proprioceptive actuator developed at MIT. This motor can sense force through its own electrical feedback. It feels the ground without external sensors. When a proprioceptive motor touches the ground, it instantly knows how hard. It can push back with exactly the right force. It can absorb shocks without breaking. The key innovation was torque density, how much force a motor generates relative to its weight. The MIT motors use wide, thin designs that maximize torque in a compact package. This is counterintuitive. Most motors are cylindrical, optimized for spinning. The MIT motors are flat, optimized for pushing, different shape for a different job. Let me explain why terrain is so challenging. Walking on a flat floor is solved. Walking on unknown terrain, rubble, grass, ice, stairs, remains at the frontier of AI research. Each surface has different properties. Concrete is hard and predictable. Sand shifts under pressure. Ice is slippery. Grass hides holes. The robot must adapt instantly. Computer vision adds another AI layer. Convolutional neural networks, CNNs, process camera images to identify terrain types. Depth cameras and LiDAR create 3D maps of the environment. Vision transformers, VITs, are increasingly used for terrain understanding. They can recognize complex patterns like stairs, curbs, and obstacles that require different locomotion strategies. But vision alone is not enough. MIT's Cheetah robot demonstrated blind locomotion, climbing stairs without cameras, sensing each step through its feet using only proprioceptive feedback. Blind locomotion uses recurrent neural networks, RNNs, or temporal convolutional networks to process sequences of proprioceptive data. The robot learns to feel what it cannot see. The most impressive demonstrations combine both approaches. Vision predicts the easy parts, touch handles the surprises. Multimodal fusion networks integrate both sensor streams. Energy efficiency matters enormously. A robot that drains its battery in 20 minutes is useless for real work. Efficiency determines practical deployment. Humans walk at roughly the metabolic cost of 2 watts per kilogram. Early robots like Asimo used over 10 times that amount. The gap represented wasted energy. Modern robots are closing this gap by using passive dynamics where possible and active control only when necessary. They approach biological efficiency. RL policies can be optimized explicitly for energy efficiency. Here is a key insight. Building a robot's cerebellum, the balance system, is harder than building its brain. Logic is well understood. Balance involves complex dynamics that AI is only now mastering. This is why the locomotion problem has attracted so much AI research attention. Solving it unlocks robots that can go anywhere humans go. That is the holy grail of robotics. The companies that master bipedal locomotion will dominate the humanoid robot market. The AI and engineering science we covered today is the foundation they are building on. For Kazakhstan, understanding this science matters because it reveals what is hard and what is becoming commoditized. Locomotion solutions are spreading, integration opportunities are emerging. Consider Kazakhstan's terrain: steppes, mountains, extreme weather, industrial sites. Robots that work in a California warehouse may fail in a Kazakh mine. Locomotion science explains why. Temperature affects battery performance and motor efficiency. Snow and ice change traction requirements. Dust and sand clog mechanisms. Each environment poses distinct locomotion challenges. The entrepreneurs who understand these constraints can specify what their applications require and evaluate whether available robots can deliver. This is valuable knowledge. Robotics is moving from laboratory curiosity to industrial deployment. The companies that deploy successfully will be those that match robot capability to environmental reality. One final point: the AI models keep advancing. What was impossible last year becomes possible this year. Staying current with locomotion research helps you anticipate what applications become viable. Follow the research from MIT, Berkeley, ETH Zurich, and Chinese universities. Watch what Boston Dynamics and Unitree demonstrate. The frontier moves quickly. Your understanding of locomotion science positions you to evaluate opportunities that others miss. When a new robot appears, you can assess its capabilities based on engineering and AI principles, not just marketing claims. For your Smile participation, generate 3 what-if hypothetical scenarios related to bipedal locomotion that could potentially lead to patents or entirely new solutions. Think about unsolved problems, unexpected combinations, or novel applications. For each scenario, state the what if question, explain why current solutions do not address it, and describe what breakthrough it might enable. Post your 3 hypothetical scenarios and comment on 3 peers' scenarios, building on their ideas or identifying challenges. Evaluate based on creativity, technical grounding, and innovation potential. Sample smile posting. Hypothetical 1. What if a robot could change the stiffness of its legs in real time like an octopus changes its arm rigidity? Current motors have fixed compliance. Variable stiffness actuators exist but are heavy and slow. A lightweight, fast-switching variable compliance system could enable robots to walk softly on wooden floors, then instantly stiffen for jumping. Potential patent: bio-inspired variable impedance actuator using smart materials. Hypothetical 2. What if robots learned locomotion by watching videos of animals and humans without any simulation? Current Sim 2 Real requires expensive physics simulations. Video to policy learning could democratize robot training. Anyone with YouTube could train a walking robot. Potential patent: video-based locomotion policy extraction using vision language models. Hypothetical 3. What if robot feet had distributed tactile sensing like human skin with thousands of pressure points? Current force sensors give only aggregate foot pressure. Dense tactile arrays could enable robots to feel individual pebbles, detect ice patches, and adjust micro grip in real time. Potential patent: high density, flexible tactile skin for robot feet with integrated neural processing. This knowledge compounds. The student who understands locomotion today becomes the professional who makes good robotics decisions tomorrow or who invents the next breakthrough.